Okay, well, let's thank Roger again. And so the last talk of the morning session is the talk left over from yesterday, and the title is Titan Tholins, How Laboratory Experiments Supported the Cassini Huygens Mission by Thomas Gautier. Thomas.
Thank you. So yeah, I've been asked to give you a talk about Tholins and how we used laboratory experiment to support the mission through the years. So just a very quick introduction. I'm sure most of you know this already. Titan is extremely hazy, which makes it very interesting, also complicates a lot measurements, especially from the orbit, but also from in situ. And so this haze particle, just very brief summary, they're here because you have this nitrogen and methane, which in the upper atmosphere can be ionized and dissociate by solar photon or energetic particle from Saturn. And they're going to react to form volatile, light volatile, which themselves can react to form larger molecule and so on until you end up with solid particles. So this talk is only about Tholins, which are by the definition that came to be a consensus over the past few years, laboratory analogs of Titan aerosol. So they're lab-produced samples that try to replicate this extremely complex chemistry, which is this fascinating chemistry where you start from just two very simple molecules, nitrogen and methane, a little bit of energy, and you end up with probably the most complex organic material in the solar system. And so if you want to do that in the lab, it's actually quite simple. All you need is just a box where you're gonna introduce a gas that's represent Titan atmosphere, so just nitrogen and methane, and you bring energy. Could be photons, could be electrons. And if you do that, you eventually gonna form Tholins. Of course, you can complicate things a lot and add like temperature control, in situ measurement, sample collection, ex situ analysis. But if you just want Tholins sample, all you need is a box and some gas and a pump. And so a few years ago, Patrice Coll put this review about the different setups that have existed historically to produce Tholins and Titan analogs in the lab. And I went last week to look at which one was still active. And pretty much all of the historical one have been deactivated since then. But hopefully there have been quite a few new setups, both in the US, in Europe, and in Asia. And so today I'm gonna focus mainly on the three big setups that have been active for the past 10, 15 years, which are Cosmic at NASA Ames, Phaser at Johns Hopkins, and Pomp in Paris. But obviously there's still a lot of other research going on. Some newer generation reactors are being set up, have been set up in the past few years. And again, for the sake of time, I'm just gonna be focusing on gas phase reaction today. So the higher atmosphere formation of aerosol. But there's a whole other field looking at HICE Tholins and HICE irradiation of what can happen when you go down in the stratosphere or the higher troposphere. So just to give you a few examples of how we used this kind of experiments to support Cassini and Huygens and interpret the flight data. So the first one will be on the aerosol optical properties. So with DISR, Thomas et al. Were able to retrieve this phase function, scattering phase function of the aerosol. So basically how the aerosol scatter the light at different angles. And to do that, they needed real and imaginary part of the refractive index of the aerosol. So to do that, they used the N and K from laboratory experiments, which were determined by canonical experiment that I'm sure a lot of you have heard of from Carey et al. 1984, which was extremely helpful through the entire mission. Also just want to point out that since then, there have been a lot of different optical measurement on Tholins. There's a much more recent measurement on this. Don't hesitate to use it as well. So basically, this was one way the optical measurement helped DRSA. When we look at VIMS and SIRS, Vinati et al. Observed in the SIRS data 3 bands that you have here that were attributed to carbon-hydrogen bands. And when looking at laboratory Tholins, which you have in in black here, we were able to confirm that these were indeed aliphatic carbons function in the aerosols themselves. Another way laboratory studies were extremely helpful was to look at the aerosol formation mechanism. So especially both CAPS and INMS revealed a huge complexity in the chemical composition of the higher atmosphere. So here you have a typical INMS mass spectra in the high atmosphere. And this complexity can be reproduced in the laboratory. So on the right here, you have mass spectra obtained on the phaser setup, which is at Johns Hopkins, where you can see that the gas phase composition in the experiment replicates the complexity of what's observed by Cassini. Of course, we don't always see exactly the same peaks or exactly the same concentration of molecules, but this is extremely helpful to identify key molecules in the pathways for the growth of aerosol. Another example is if you look at the Cassini CAPS measurement, which you have here on the left with ELS instrument and CAPS IBS on the right. And if you compare CAPS IBS, which is in red, to laboratory spectra measured in the cosmic setup at NASA Ames, again, you can see very strong similarities, sometimes also dissimilarities that allows you to identify what's missing in your laboratory experiment. And that really helps identifying key species in the chemistry leading to this aerosol. The last case, another case, regard aerosol composition. So as Paul presented this morning, ACP aboard Huygens detected principally actually only HCN and ammonia, which was highly debated. But when you do laboratory experiment reproducing the ACP experiment where you parallelize laboratory Tholins, what we do is that the two main products are HCN and ammonia. So that is a very strong confirmation that the ACP results are done to what should be seen with this kind of experiment. I'm just going to take a very side step here, a very quick side step here, because we were talking about ACP, which was connected to GCMS. So Paul also presented this morning GCMS result. And this is more a general note to everyone who's worked on Huygens and Cassini, is that the numerical methods to treat the data have strongly evolved also in the past 15, 20 years. And there's a lot of things we can do new with the same data. So this is just an example of work we've done recently, and Francis talked about it also a bit yesterday, where we reanalyzed GCMS data. And with the same data, basically, we were able to increase the vertical resolution of the methane profile by a factor of 30 or even 50 in some areas. So if we go back to Tholins, one thing laboratory experiments also have strong advantages on is that they're here, they're in the lab. So basically, it's like a free sample return. So we can take our sample and use state-of-the-art analytical technique to look at what they're made of, how they're made, and understand the chemistry and the physics of this aerosol. So these are just two examples of here, typical mass spectra of Titan Tholins produced in the lab. And you see that with Cassini data, we see a huge complexity, but if you push it with state-of-the-art instrument in the lab, actually you see molecular peaks at every single mass up to mass 1500 or so. There's literally tens of thousands of different molecules in the Tholins. This is analysis made by Melissa Ujlo and Melissa Trainer at Goddard, where they were able to follow the isotopic fractionation in the inclusion of the aerosol through following it in the gas phase and showing that this fractionation is reaction dependent and trace back which pathways lead to isotopic fractionation in this atmospheric chemistry. Other examples of things we can do in the lab that Huygens was not able to do is, this is a recent paper by you et al. Where they measured the contact angle between tholins and liquids. And this is extremely helpful for microphysical model to model the formation of clouds and how these aerosols are gonna interact with each other as they precipitate through the atmosphere. And finally, the last one on the right, this is my personal favorite, is what we could have seen on Titan if we had sent a AFM, so atomic force microscope, which of course weighs several tons and it's not doable. But this is a picture of tholins at the atomic level. So the lines you see here, these are covalent bonds between atoms, and you actually image the exact molecules in your sample. Sorry for that. So of course, there's still challenges even in tholins. And the main one of the main one is the size of the aerosol. Cassini and Huygens data showed that monomers are fairly small, like around tens of nanometers. In the laboratory, pretty much all the samples we produce tend to be hundreds nanometer or micron size. Another one that I didn't address today is the fate of the aerosol when they reach the surface, and this will be particularly key for Dragonfly. There have been a lot of experiments in the late 90s, early 2000s about hydrolysis of tholins in liquids, be it water or ammoniated water or something like that. And I think it would be extremely helpful to reactivate these kind of studies in the coming years in preparation for Dragonfly. And the main challenge for me, the main thing I personally don't understand is the nitrogen incorporation. So what we see, what every single team that do tholins see is that we have a lot of nitrogen in the tholins. What we see is that if we don't have nitrogen, it is extremely hard to produce tholins. And actually, Jonathan presented this picture this morning that I snapped from your presentation. And there's something that was really attracting to me is that pre-Cassini, you had an estimation of up to 1 kilometer photolysis product. We know that the photolysis, the aerosol layer is several hundreds kilometers, and that's because of nitrogen. And I'm honestly deeply convinced of that without the nitrogen chemistry, you cannot have an efficient aerosol factory like you have on Titan. Yet, if you look at Cassini data and Huygens data, besides the ACP result, we do not see nitrogen in the aerosol. So neither VIMS nor SIRS saw any evidence of nitrogenated gas. So this is, to me, one of the main remaining questions on this aerosol composition. In terms of lesson learned, so lab studies, I think, proved to be helpful with Cassini. We also saw that they take a lot of time, think about several years from the moment you conceptualize your experiments, get the funding, do the experiment, process the data. And so they need to be started early on. One thing that was extremely helpful when it happened was having embedding laboratory people in the instrument team or instrument people in the laboratory team, because that allows for a faster turnaround of what is exactly required by the mission as input data for the interpretation. Another key point is we realized through the year that cooperation in Tholins field, I'm talking it's a laboratory field, was much, much more effective than competition. When I started in the field, I remember each team were like, hey, my sample is the best. No, my sample fits this band better. Or mine is better, we slightly better in temperature reproduction or things like that. Later paper in the Tholins field takes sample from many different teams and applies the same analytical procedure to try to derive key features on the sample. The reason for that is that Titan aerosol analogs are just that. They are analogs. They're not aerosol. They're not perfect. They don't reproduce perfectly what we see on Titan. There are tools to help interpret what we see. And the more tools you have, the more way you have to understand the exact mechanism which are at play on the planetary body. And the last thing is also that this kind of lab studies, which were, for most of them, started for Cassini, also had a strong heritage toward further missions, and especially New Horizon and nowadays James Webb, where these experimental facilities are used to routinely produce atmospheric aerosol and study the properties. So I just want to thank all the people in the Tholins community. Actually, before this talk, I sent an email to most of the people I know in the community who responded very enthusiastically, sending pictures of setup, and which was, I think, as I said, we grew through from a competition phase to a cooperation phase, which is extremely beneficial for the entire laboratory community now and for future mission. And one last point, more personal, I don't have any picture from the Cassini era to show. And the reason for that is because when Huygens landed, I was in high school. And so I was not definitely in the team. But Huygens was probably one of my first exposure to planetary science through the press. And I was fascinated by it. And that's probably the first time in my life where I went, hey, looks cool to be a planetary scientist. Maybe I should do that. So on a very personal note, but I'm sure a lot of younger folks in the room would agree with me, I also wanted to thank all of you who were involved in the mission at that time for all the science you brought us and all the dream you also let us have.
Thank you very much, Thomas. Quick question before lunch.
It's okay if everybody's hungry.
Hi, I noted the aerosol sizes. Upper, in the upper atmosphere at Cassini altitudes in the ionosphere, we see smaller grains, you can call it, more like a few nanometer, and they are charged 1 or 2 charges negatively. So
sorry, so your question is about is? I'm not sure I quite got what the question was. Yeah, so indeed we see with CAPS very high altitude this heavy ions and charge, and the thing that's pretty clear, I think, to a lot of people is if you have a molecule with a mass of 1,000 or 10,000, yeah, this is not gas phase. This is solid phase. Okay. This is solid phase, probably aerosol, and yeah. So this is the kind of thing we try to reproduce in the lab.
Okay, well, thank you very much, Thomas. Can we thank Thomas and all this morning's speakers?